When you picture a library, you probably think of a nice, quiet room just packed with books. But what you're really looking at is this incredible feat of information science, a system designed from the ground up to keep absolute chaos at bay. So let's pull back the curtain a little and explore the hidden science behind how we organize pretty much all of human knowledge.
I mean, really think about it for a second. You have millions of individual items, right? And yet you can walk in, look up a specific book, and find it. How on earth is that possible? Well, I can tell you it's not magic. It is the result of a really rigorous scientific process. For the longest time, organizing books was seen as more of an art form. It was this thing that a few brilliant minds did using their own intuition and personal flair. But that kind of approach just doesn't scale, and it's not very objective. The real breakthrough came from pioneers like S.R. Ranganathan, who completely transformed classification from an art into a proper science by creating a system with clear laws and principles that anyone could follow. So how did he do it? Well, to make the whole process scientific and repeatable, Ranganathan broke the entire job down into 3 distinct stages, what he called planes. This framework is what takes us all the way from just a raw idea in someone's head to that little number you see on the spine of a book. Let's walk through them one by one.
Okay, first up, we have the idea plane. Think of this as the blueprint for everything else. It's really the most important intellectual part of the job, where we decide on the fundamental structure for our entire map of knowledge.
So before you can even think about labeling anything, you first have to really understand the subject itself. What makes it tick? What are its most essential parts? This whole stage is about choosing the right characteristics to break a subject down into useful logical categories.
To see what I mean, let's use a super simple example. Let's say you have a big room just full of bicycles. How do you even start organizing them in a way that makes sense? Well, you have to pick a characteristic to start dividing them up.
And this is where it gets really clever, illustrating a core principle called the canon of differentiation. See, if you choose number of wheels as your characteristic, you failed because, well, all bicycles have 2 wheels. You haven't actually differentiated anything. But if you choose type of rider, all of a sudden you get these really useful subgroups: men's bikes, women's bikes, and kids' bikes. Now that is a good characteristic.
All right, so once we've used these good characteristics to create our groups, the next step is to arrange them logically. And this is typically done in 2 primary ways, by creating what we call arrays and chains.
An array is really simple. It's just a set of items that are all of equal rank. The continents of the world are a perfect example, right? None of them is part of another one. They're all peers in this same category. So Asia, Africa, Europe, they form an array.
A chain, on the other hand, is all about hierarchy. It's a sequence that moves from the really general to the really specific, where each link in the chain is a subgroup of the one before it. The family tree example here, grandfather to father to son, is a perfect way to picture it. And here's a great real-world example of a classification chain. We start super broad with Asia. Then we narrow it down to South Asia, then India, and we keep going, all the way down to the specific city of Amritsar. Every single step is a logical move from a larger whole to a smaller part. That's the principle of decreasing extension right there in action.
Okay, so we've built our conceptual blueprint. We know how things relate to each other. Now we move on to the second stage, the verbal plane. This is where we give all our organized ideas some precise official names.
The verbal plane is all about terminology. Its whole job is to take those abstract concepts we just structured and assign them standardized, crystal-clear names. And this is so important because if the names are even a little bit fuzzy, the entire system can just fall apart.
Now, you're probably thinking, why can't we just use regular words? Why do we need a whole special plane just for this? Well, the big problem is that natural, everyday language is wonderfully messy, and often it's really ambiguous.
See, our everyday language has 2 huge problems for a scientific system. First, you've got homonyms, one word but with lots of meanings. If I say cricket, am I talking about the sport or the insect? And then you have the opposite problem, synonyms. You have multiple words that mean the same thing. Are we talking about wages, pay, or salary? For a classification system, that kind of ambiguity is a total disaster.
So the whole point of the verbal plane is to create a scientific language where there is a perfect one-to-one match. One single concept gets one and only one official term. It just eliminates all the confusion.
All right, we've got our structure and we've got our precise terms. Now we get to the final, and probably the most visible part of this whole journey, the notational plane. This is where we finally create the code.
The notational plane is basically a system of shorthand. It takes those standardized terms from the verbal plane and translates them into a super compact series of symbols. And that code, that is exactly what you see printed on the little sticker on the spine of every single library book. It's the part of the system that does the final bit of work.
But why go to all this trouble? Well, there are some really good practical reasons. For one thing, subject names are often way too long to fit on a book spine. Also, names change over time. Think about how Ceylon became Sri Lanka. Different languages also have different words for the same thing, and maybe most importantly, if you just used words, related topics like algebra and geometry would be scattered all over the library. A numerical code just neatly solves all of these problems at once.
And this right here perfectly illustrates one of the most elegant parts of a good notational system, something called the canon of relativity. Just look at how the number gets longer as the subject gets more and more specific, going from library science all the way down to authority files. The length of the code itself visually shows you how deep you are in the hierarchy. It's like a map of knowledge, right there in miniature.
Let's walk through one more quick example, this time from the famous Dewey Decimal System. We start with 500 for the broad category of science. We add a 1, and now we're in mathematics. A 6 narrows that down to geometry, and as we keep adding more digits, we get more and more specific. You can see how the notation is a direct reflection of that conceptual chain we built way back in the idea plane.
So we've made the whole journey from a pure idea all the way to a number on a book spine. But why does this super-structured three-plane system actually matter?
Well, let's just do a quick recap of the journey. In the idea plane, we created the intellectual blueprint. Then, in the verbal plane, we attached clear, unambiguous language to that blueprint. And finally, in the notational plane, we converted all of that into a simple, powerful, and universal code. It's this incredible system for turning abstract thought into tangible, physical order.
And this kind of leaves us with a final thought, doesn't it? This really elegant three-step process was designed to organize the entire world of physical books. But in our modern age of complete digital chaos, with our endless files and folders and emails, you have to wonder, could these same principles of classification help us finally bring some order to our own digital worlds?